Have you ever had to slam on your brakes and just wonder what happened? How all that works? It feels like magic, right? But the science behind stopping a 2-ton car is actually one of the most critical systems in your vehicle. So today, let's dive in and explore exactly how it's done. I mean, really think about it. We're talking about 2 tons of metal, thousands of pounds, just cruising down the road. How in the world do you bring all of that forward momentum to a dead stop safely in a matter of seconds? It's a huge challenge. Well, the answer all comes down to a fundamental law of physics. See, a moving car is absolutely loaded with something called kinetic energy. And to stop that car, you can't just delete that energy. It has to go somewhere. It has to be turned into something else. And that's the whole secret right there. Your car's braking system is basically a giant, powerful energy converter. Its entire job is to take all that energy of motion and transform it into heat. A whole lot of heat, actually. All thanks to the simple but incredibly powerful force of friction. Okay, so before we get into the nuts and bolts, the actual hardware, let's first understand the invisible forces that are at play every single time you even think about touching that brake pedal. So when you brake, especially if you brake hard, all the car's inertia, its tendency to keep moving forward, doesn't just go away. It causes a massive shift of the car's weight right onto the front wheels. This is a totally universal phenomenon, and it's called dynamic weight transfer. Oh, you've definitely felt this. You know that feeling when you brake hard and the front of your car just seems to dive down while the back end gets kind of light? Yeah, that's not just in your head. That is a very real, very dramatic transfer of weight onto the front axle. And believe me, this physical reality has huge, huge implications for how brakes are designed. And the consequence of that weight transfer is, well, it's pretty huge. Because so much of that weight is now pushing down on the front tires, the front brakes end up doing the vast majority of the work. We're talking around 70% of the total stopping. And that is exactly why the front brakes on your car are almost always bigger and more powerful than the ones in the back. All right, so creating friction is the name of the game. But how does a relatively simple press of your foot generate enough raw force to stop a 2-ton vehicle in its tracks? Well, the answer is the elegant and frankly brilliant power of hydraulics. At the very heart of the system is a component called the master cylinder. The best way to think of it is as a force multiplier. It takes that pretty light mechanical push from your foot on the brake pedal and through the magic of hydraulics converts it into incredibly high pressure inside the brake fluid. And here's a really crucial safety feature you'll be glad you have. Modern master cylinders aren't just a single pump. Nope. They have what's called a tandem design, which means they're actually operating 2 totally separate hydraulic circuits. So what happens if a brake line breaks and one of those circuits fails? You don't lose all your brakes. The other circuit is still there to bring you to a safe stop. It's just a brilliant piece of redundant engineering. And all of this happens in the blink of an eye. Your foot presses the pedal, that gets converted into hydraulic pressure, which shoots through the brake lines. And because brake fluid can't really be compressed, that force arrives at all 4 wheels at pretty much the same time, activating the clamps that create the friction. It's simple, it's elegant, and it is incredibly effective. Okay, now we get to the business end of the whole system. The actual hardware at the wheels that's responsible for generating all that friction and all that heat. You'll generally find 2 main types out there, disc brakes and drum brakes. Now, disc brakes are pretty much the modern standard, and for a really good reason. You've got a caliper that squeezes brake pads against a spinning disc or rotor. The key advantage here is its open design. See, heat is the #1 enemy of braking. Too much heat can cause a super dangerous situation called brake fade, where you lose stopping power. The open design of disc brakes lets all that heat escape quickly, which means you get consistent, reliable stopping power time after time. Drum brakes, on the other hand, work from the inside out. You've got brake shoes that push against the inner surface of a drum. But their biggest weakness is that enclosed design. It traps heat, which makes them much more likely to suffer from that brake fade we just talked about. So why are they still around? Simple. They're cheaper to make, and it's really easy to integrate the parking brake mechanism right inside. So they're still a popular choice for the rear wheels on a lot of cars. So when you look at them side by side, it really comes down to a trade-off. If you want the best heat dissipation and the most consistent performance, disc brakes are the clear winner, no question. But for cost-effectiveness and packaging, especially on the rear axle, drums still have a role to play. But yeah, when it comes to pure, raw stopping power, discs are king. But the story doesn't just end with hydraulics and metal parts.
In the last couple of decades, braking has gotten a whole lot smarter. We're talking about a whole suite of electronic safety systems that basically act like a guardian angel watching over you.
Have you ever been in an emergency situation where you had to just stomp on the brakes? And did you feel this weird, rapid pulsing or vibration coming up through the pedal? If you have, don't worry, your car isn't broken. That's actually the feeling of your anti-lock braking system, or ABS, doing exactly what it's supposed to do.
So, what is it actually doing? Well, back in the day, before ABS, if you slammed on the brakes, your wheels would just lock up solid. And a locked, skidding tire gives you zero steering control. You're just a passenger at that point. ABS prevents that from happening. It keeps the wheels rotating right on the verge of locking up, which gives you maximum grip, and this is the most important part, it allows you to actually steer while you're braking hard.
And just how fast does it do this? A computer is sensing the speed of each wheel, and if it detects one is about to lock, it can pulse the brake pressure on that specific wheel up to 15 times a second. That is faster than you can blink. It's a truly superhuman reaction that keeps you in control when you need it most.
Now, building on that same ABS technology is something called electronic brake force distribution, or EBD. Think of it as a smarter version of ABS. It's constantly looking at your speed and how the car is loaded, like if you have passengers or stuff in the trunk, to perfectly balance the braking force between the front and the rear wheels. This stops the rear wheels from locking up and gives you the most stable, efficient stop possible in any situation.
And one more for you. Brake assist. This whole system is designed to overcome a very human problem: hesitation. Studies show that in a panic stop, a lot of drivers just don't press the brake pedal hard enough. So brake assist doesn't measure how hard you press, but how fast you press. If it senses you've slammed your foot on the brake in a panic, it automatically takes over and applies full braking power for you, which can shave critical, life-saving feet off your stopping distance. So let's tie this all together. At its core, braking is just energy conversion, turning motion into heat. The hydraulic system multiplies your foot's force to make it possible. Disc brakes are the best at getting rid of all that heat. And finally, all those smart electronics, like ABS, are there to make sure you stay in control during an emergency. And all of this kind of brings us to a pretty fascinating thought, doesn't it? We've gone from simple mechanics and hydraulics to intelligent electronic brains. And now we have cars that can literally brake all by themselves to avoid a collision. So it really makes you wonder, what does the future of stopping even look like? What's the next big leap going to be? Something to think about. Thanks for joining me on this one.